Hi students, in this video I want to talk about dimensional analysis. First, dimensions are basic type of units such as time, length, mass. Any mathematical equation relating physical quantities must be dimensionally consistent. So let us explain what this means, right? So we can add quantities only if those quantities have the same dimensions. So this is what is basically to be dimensionally consistent. You can add, for example, 2 meters and 3 inches. After, of course, make the conversion either to meters, the meter 2 inches or the inches to meters, but you cannot add 2 meters and 3 kilograms because those are quantities, that are not dimensionally consistent. In the examples I will give you here, they say determine whether the equation is dimensionally consistent. And they give us here in brackets uh, some symbols that are representing the dimensions of that quantity. For example, ds in brackets, represents the distance, and the unit is L because it's a unit of length. The velocity in brackets, the units are units of length and time to the -1. The acceleration are units of length and time to a -2. And the time has just units of time. So units of length we represent with L, unit of time we represent with T, unit of mass we represent with an M, and in this case when we have, for example, velocity, we say L T to the -1. That is going to be the same that L over T because it's meters per second, for example. So it's units of length divided by unit of time. So they say here that we make an analysis, to see if these are dimensionally consistent. Okay, so what are we going to do first? We're going to rewrite, this equation using the dimension. So we're going to say here that this is b squared is going to be b times v equals 2 times a times s. Which are the units of velocity? L t to the -1, times, again, L t to the -1 equals, any constant will be replaced by 1 times the acceleration replaced by L t to the -2 times distance, that is L. So L times L would be L squared. T to the -1 times T to the -1 would be T to the -2. And in the other side, we have L times L, L squared, and T to the -2. So as we see here, we have the same thing on both sides. So this equation is dimensionally consistent, right? Let us see the next one. So we have distance here equals, we have velocity times the square of the time plus 0.5 times the acceleration times the square of the time. So distance is in unit of length. Velocity, we know that is length times to the -1 times t is time to the second power, because it's t squared, plus 1 times acceleration, that is L t to the -2, and then we have t squared again. So we have L here, so I have L t to the -1 times t to the second, adding the exponent we get just t to the 1, so this is just t. So we get Lt plus And then here we have 1 times L, that is going to be L. T to the negative 2 times T to the second will be T to the 0. So this will be L equals LT plus T to the 0 is 1 plus L. So this is not dimensionally consistent. This one is yes, is dimensionally consistent in both sides. We had L to the second T to the negative 2. In this case, it's not dimensionally consistent because in one side we have L, and the other side we have L times T plus L. So this second case is not dimensionally consistent. Let us analyze this other case. We have now here B equals S over T. So we can say, okay, B equals S over T. So which are the units of velocity? L, T to the negative 1 equals, which are the units of distance? L, length, over the time. So I represent with this T. Of course, if we want to move this up, we can say L T to the negative 1 equals L T to the negative 1 here. So this one is dimensionally consistent because in both sides we have exactly the same thing. Let us see our last case is acceleration equal velocity divided by time. So we use the brackets around the symbol, to represent the dimensions of the quantity. So I say symbol of the acceleration is in brackets equals, the velocity here in brackets, divided by the time. Now, which are the units of acceleration? Acceleration is equivalent to L T to the negative 2 equals velocity is equivalent to L T to the negative 1 and T is equivalent here to the T because it's units of time. So we bring this T up here, reversing the sign of the exponent. So we have L T to the negative 2 equals L T to the negative 1 times T to the negative 1. So L T to the negative 2 is equal to L T to the negative 2 because T to the negative 1 times T to the negative 1 is going to be adding the exponent T to the negative 2. So this case is also, yes, it's dimensionally consistent because in both sides we got exactly the same thing. So this is basically, what the dimensional analysis is. So remember that every time that we work with an equation, we have to make sure that the equation is dimensionally consistent.